Good morning, campers. Morgan here. So, we're going to be talking about the kinetic molecular theory of gases today, one of my favorite all time subjects. So, let's imagine that we've got a balloon, and that balloon is closed, and it's full of a gas. We can make it helium. Okay, nice simple atom. All right? And it's at some temperature, which we will creatively call T, and that has a volume, which we creatively call V. Now, here's the question. Do all of those particles of the gas that are inside that balloon travel at exactly the same speed? And the answer is no, they do not. Okay? They have an average speed. Now, we know that temperature is directly proportional to the Kelvin temperature of the particles that are in that balloon. Okay? Now, we will understand that the majority of those gas particles are all traveling at the same speed. But I cannot tell you how any one specific particle is going to behave. It might be part of the average. It might be faster, it might be slower. There's no way to know how one particle behaves. However, it's perfectly reasonable for us to talk about the behavior of the majority of the particles. Okay? And this is actually the beginning of something that we call statistical mechanics. Now, the ice cream graph. The ice cream graph, that's not a technical name. Sorry. Okay, so we're going to do a plot here. Now we're going to put speed on this axis, and we're going to put the number of particles on that axis. Well, they're on the y. Now, let's imagine at first that our balloon is at a relatively low temperature, like room temperature. We're going to get a distribution of velocities that looks something like that. Okay? And we'll say that's at T1. Now, I've drawn it in blue because it's the cooler temperature. Now, if I raise the temperature to T2, and we know that T2 is greater than T1, what we can say is that the average speed has increased. We've still got the same number of particles, that hasn't changed, but at the lower temperature, T1, this is the speed they're moving at on average, and at the higher temperature, T2, that's the speed that they're moving at on average. More of the molecules have faster velocities at the higher temperature than at the lower temperature. However, we still have the outliers. We still have some that are very slow and some that are very fast. It's just not very many of them. Okay. Now, also take into consideration that if the gases were, or if the particles in the gas were not all the same, these would be different. My argument here is contingent upon all of those particles being the same, all helium atoms in my example. Okay. Now, let's picture a balloon now to illustrate something called Dalton's law. And it contains air. Now, air is not just one compound. There are three different gases, okay, in air. We've got nitrogen, mostly, oxygen, and the third most prominent, believe it or not, is argon. So, the total pressure P total in the gas that's in our balloon, which is just air, will be the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon. See, pressure is caused by the particles in the gas colliding with the walls of the container. And we can't sit here and go, oh, that one was from a nitrogen, or oh, no, that one was from an oxygen. That's not possible. Okay? The collisions just happen, it causes pressure. So, in general, we say the total pressure is P1 plus the P2 for the second gas plus P3 plus whatever, however many gases we might have mixed in there. Okay? Now, if we've got a balloon that's got argon at 1 atmosphere and helium at 1 atmosphere and nitrogen at 10 atmospheres, the total pressure in there equals 1.00 atmospheres plus 1.00 atmospheres plus 10.00 atmospheres, which equals a total of 12.00 atmospheres. I just can't tell the difference between which particles are causing the pressure. I just know the fractions. Okay? Now, we're assuming that all of these are at the same volume and temperature. Is that safe? Yeah, they're all in the same container. So if they're all in the same container, they'd all be the same volume, and that container's at one specific temperature. So those things are the same. However, what can be different, though, is the number of the particles present. And we know that you have the most particles for the gas that's at the highest pressure. It's causing more pressure because it has more collisions with the walls of the container. All right. Let's move on. We're going to talk about effusion versus diffusion. Now, if you've seen the motion picture called The Martian with Matt Damon, there's a pretty cool scene at the end of it where he's trying to get from one spaceship to another spaceship. And he pokes a hole in his glove, which is in his spacesuit, pressurized. And gases shoot out of that glove. And he kind of pretends to be Iron Man out in space. Okay? Now, there's actually a name for what that gas is doing. We need to distinguish between diffusion and effusion. Now, if you exhale right now and the air that's in your lungs comes out, it mixes with other air that's out and surrounding, your body. That's called diffusion. That's a mixing of gases. Now, the gas particles that you're exhaling don't really interact with the gas particles that are outside your head. See, it turns out the gas particles that are outside, all gas particles really, have pretty big distances between them. Okay? And they travel long distances before they hit each other. There's a name called, it's called the mean free path. Okay? Now, that means that they're pretty much independent of each other. Okay? Now, in effusion, we say this is the passing of a gas into a vacuum. So that was what Matt Damon was doing when he poked a hole in his spacesuit and the air in the suit was flying out, because surrounding him there was a vacuum. There's just nothing there. Now, it turns out both of these behaviors are basically the same because the distances between the particles are great. Now, there's no particles here, so there's no interaction, but the distances between the ones in diffusion are so great that there's also no interaction. Okay. So, if we have gas molecules that have different masses, which ones move faster? Let's compare helium and uranium hexafluoride. Helium, UF6. That's got a molar mass of 4. That's got a molar mass that's up over 300. Okay? Helium's faster because it's lighter. Uranium hexafluoride is slower. Okay? Really important concept there. All right? Now, however, they're under conditions of identical temperature. So what that means is their kinetic energies are the same. So the kinetic energy of gas A is equal to the kinetic energy of gas B because they're the same temperature. So if kinetic energy is equal to 1/2 the mass of the gas times the velocity squared, we can say that 1/2 the molar mass of gas A times the velocity of gas A squared is equal to 1/2 the molar mass of gas B times the velocity of gas B squared. The 1/2s will cancel, and doing a little bit of algebra, the molar mass of A divided by the molar mass of B is going to equal the velocity of gas B squared over the velocity of gas A squared. And this is very often presented actually as the square root of the molar mass of A over the molar mass of B equals the velocity of B over the velocity of A. Okay. What is this saying? It's saying the lighter gases move faster and the heavier gases move slower. So let's imagine we got some helium. It's diffusing at a rate of 15 milliliters per minute. How fast would nitrogen diffuse under the same circumstances? Well, rearranging this equation, we just have to identify which gas is A and which gas is B. Okay? So, why don't we solve? We're going to solve this for B. Velocity of B squared equals the mass of A times the velocity of A squared over the molar mass of B. Okay? We'll make helium gas A. We'll make nitrogen gas B. Okay? So the molar mass of helium is 4.0 grams per mole. Get that off the periodic table. And we were told it's moving at 15.0 milliliters per minute, which we're going to square. And then, sorry, my 1 didn't turn out looking so good. Let me rewrite that, 15.0. And the molar mass of nitrogen gas, that's N2. So that's going to be 28.0 grams per mole. Grams and grams cancel. Okay. So I'm going to go through, do a little bit of arithmetic, take the square root, and it turns out the whole thing turns out to be 5.67 milliliters per minute. Now, does that make sense? Nitrogen is heavier and it's moving slower. This was 15, that's 5.5. Yeah, that makes sense. The heavier one should move slower. Now, how much faster would methane, which is CH4 by the way, move than oxygen, which is O2? Well, what I'm really asking for here is to compare your velocities. The velocity of B divided by the velocity of A. Okay? Now, methane will be faster than oxygen, won't it? We should remember that. Okay? So let's make methane B and let's make oxygen A. Okay? So this equals, back up to this part, the square root of the molar mass of A divided by the molar mass of B, which equals, let's see, for oxygen, that's 32.0 grams per mole. For methane, that would be 16.05 grams per mole. Take the square root of that, the units cancel, and this is about 1.41 times faster. And it would be faster because it is lighter. Okay, so there you go. That's the idea behind effusion, diffusion, and Graham's law. Thanks for tuning in. Have yourselves a good day. This is Morgan, signing off.